Okay, I'm going to give an overview of exploratory factor analysis. So, a couple of things to start with. I would read DeVellis's chapter and I would read the Worthington article first, and then I would come back to these later on. So I'm going to give an overview of just even how to approach learning stats. So this is how I think of it. If you've ever painted a dark wall, you just know up front that you're going to have to do several coats. So you don't worry too much with the first coat. You just kind of get some paint on there, and then you know as you get closer to the end that you'll kind of fill in the gaps. So in your first coat, just kind of skim and try to get a sense conceptually of what's happening and what the big picture is. Second coat, try to get a sense of the key decisions that you're going to have to make as a researcher, and in particular, the kinds of things that may make or break whether the paper has a chance of getting accepted. And I'll try and point those out as we're going through this overview. And then third coat is actually running the analysis and kind of matching just the conceptual ideas with the behavior of kind of doing it. And then fourth coat is often going back to some of the readings and trying to fill in your gaps. And so this is kind of like you're looking for splotchy places and kind of filling in your understanding now that you kind of know what it's like to actually do the analyses. And then the last step I have listed here is actually writing something up and publishing with a particular method. And this helps because if you're writing with someone who has more expertise in the area, then they'll give you feedback and help you get your write-up correct. And then you'll get feedback from reviewers and the editor. And by the time that you finish publishing, you'll have a much deeper understanding of the method you're using. And it kind of consolidates it. So by the time you have published your first article with EFA, you've probably run the analyses multiple times, had lots of practice, had to think about it from several different perspectives. Okay, purpose. Short version is this is how you decide how many subscales are in a measure, and people use it to refine measures and cut down from an initial item set to a narrower set of items that is performing well. And DeVellis kind of gives a nice conceptual explanation of what's happening, but the short version is all of the variability of all your items. The program is assuming one factor, and it tries to do the best it can to kind of predict that variability. But then with what's left over, it creates a second factor and tries to predict the remaining variability, and it keeps going and going and going, but there's a point of diminishing returns. And so we'll talk about kind of how to determine when your next factor isn't worth it. Okay, so steps to doing an EFA, and then later on I'll show you a basic lab that you can do to kind of walk through this. But the first step is just going into the program and identifying which items go into the EFA. So then step two, there's several decisions to be made in selecting the analysis. One is the rotation method. So if there are more than one factor, you can use a method that either assumes that the subscales are orthogonal, basically they're uncorrelated, or you can allow them to correlate with each other. That's an oblique rotation. And traditionally, I've heard people strongly argue for the oblique in psychology because oftentimes our subscales are correlated, and so why not disallow them to correlate with each other? Although there are some people who would argue for the advantages of an orthogonal rotation. So selecting an extraction method, this is more technical, but Common factor analysis kind of fits the assumptions of scale development and the idea of a latent factor better than principal components analysis, but you can read up about some of these different extraction methods. Some people like maximum likelihood because it corresponds with what happens in CFA, and so might make that more likely to replicate, for example. A general rule of thumb, I kind of like this one. So deciding how many factors to extract is an important decision, and parallel analysis is still probably the preferred method, and the logic of that is you're comparing the eigenvalues, and so eigenvalues represent how much how much variability each factor is explaining in the total set of items, and there's a point at which a random data set is doing better than the eigenvalue for your scale, and that's a point where you're like, what's the point? So that's the logic of parallel analysis. The eigenvalue above one rule is somewhat similar, but it's usually a little bit more lenient. So parallel analysis, that kind of crossover tends to happen a little bit sooner. And then scree plot, the logic of that is you're kind of looking for an elbow in the plot of the eigenvalues, and there's a point at which the next eigenvalue is pretty much the same value as the prior. So this is easier to see kind of in a picture, but and we'll kind of look at that later. But these are kind of the different rules of thumb, but parallel analysis is probably the one you want to use. Step 4, interpret the meaning of each factor. So this is fairly subjective, but you kind of look at the items and you try to kind of identify what theoretical construct seems to kind of be in common across the different items. And you're kind of paying attention also to the possibility that there may be some sort of method factor that is explaining why the item's kind of pulled apart into a second factor. So an example would be if all items kind of shared a similar phrasing. Step 5, evaluate poor items. So an empirical criterion would be simple structure. So if you're using kind of an EFA, CFA kind of progression, then CFA assumes that each item loads on the primary factor and doesn't cross-load. So there's a zero cross-loading on any secondary factors. So you can use EFA to actually pick items that would perform well under those kind of assumptions. And the other thing in terms of evaluating poor items is you could, kind of on your initial sample, you could use strategies to identify a possible method factor. So there's a couple ways you could approach this. One would be to covary out the total score for the subscale and then look at inter-item correlations. And so what that means is if the items are still correlated with each other even after controlling for the latent construct, then that's evidence that there may be some sort of method factor. They're correlating too strongly with each other. The other thing you could do that would work fairly similarly is go ahead and do a CFA after you've done the EFA, and look at the modification indices. But if those items are correlated too strongly with each other, then they'll show up as kind of poor fit, and they'll suggest dropping some of those items in the modification indices in M+. So that's a little bit technical, and we'll kind of look at that together. The other thing that's more subjective is you can kind of eyeball the items, and if there are some items that just don't seem to fit theoretically with the other items on the subscale, then you might make an argument for dropping those items. Um, and then finally, step 6, once you've kind of dropped any items in the initial run through, you kind of repeat, you refactor, and make sure that all of your items kind of continue to meet criteria and that the factor structure didn't shift. So sometimes when you drop several items, you may end up, like say we had 3 factors in the prior run through, but then it actually condenses to 2. So you want to make sure that when you rerun the EFA and kind of refactor it, that your results are stable. So yeah, that's kind of an overview of EFA from what would be a study 1 in a scale development paper.